So in your lab manual, you've got this equation here, E naught cell equals E naught reduction cathode minus E naught reduction anode. This will allow you to determine which one of these is going to be the anode and the cathode. So in the case of copper and zinc, you've got a reduction potential of plus 0.34 volts for copper and minus 0.76 volts for zinc. Using this equation, we need to determine which combination will allow us to get a positive E naught cell value. As you can see here, if we make the copper the cathode, what's going to happen is that's going to be plus 0.34 and then it's going to be minus 0.76, which is going to clearly result in a positive value for E naught cell. If I switch this around and make zinc the cathode and copper the anode, then this value will clearly be negative. So that's allowing us to tell that it's going to be copper that has to be the cathode and zinc that has to be the anode. Alright, let's look at what you're going to do with some of this data. So as I've got over here, you're going to have some measured cell voltages, which are going to be what will go in your recorded data. Now if you're taking the lab online, you'll find these results in the student lab data, and that will go in here under recorded data for the standard cells, and then here for the non-standard cells. Additionally, those values will get pulled down here for the standard and non-standard cells as well. So you just take this data and put it into these boxes here for the measured voltages. Now the calculated voltage, now let me give you an example for the standard cell, and it's going to pretty much mirror what we were just talking about with regard to figuring out the anode and cathode. So what we have here are going to be reduction potentials. Now the reason we know that they're reduction potentials is because all of the electrons are on the reactant side, meaning they're all receiving electrons at this point. So that makes all of these reductions. But in order to make a cell, one of these has to be turned into an oxidation. And when we turn it into an oxidation, it flips around. So when we look at the equation that we had earlier, it was E naught cell is equal to the E naught for the cathode minus the E naught for the anode. And effectively what we're doing there, and these are both reduction potentials of course, and what we're doing here if we're subtracting is we're flipping it around, turning it into an oxidation. So you can think of this minus as being like a plus negative if you want. That's the other way of looking at it. So the way we can look at the E naught for the cathode reduction, we've got the cathode being the copper, and we can see that that's 0.34 volts. Now the zinc, we're flipping around, turning it into an oxidation, and when we do that we get minus 0.76 volts turning into plus 0.76 volts. So you can see what we've done is we've flipped it around, and which changed the sign here, and that gave us a positive value for the E naught cell, which is what we wanted in the first place. The total reaction there is going to be this. Cu2 plus zinc gives zinc 2 plus copper. And the way that we'll get the E naught cell value is simply by adding these two voltages together, and this will be the calculated voltage for our standard cell. This will always be a positive value, and if it's getting it as a negative value, it means you flipped the wrong thing. But remember, all of these are reduction potentials, and when you flip them around you turn it into an oxidation. A standard cell has to consist of both a reduction reaction and an oxidation reaction. So here we have a multimeter, and what Sam's going to do now is going to plug in the electrodes into that multimeter. So what he's going to do is he's going to plug the red one into the middle one there, which is going to be the positive, and the black one into the negative, which is down the bottom. Now what he's going to do is he's going to take the other ends now and remove the caps of these electrodes. And now he's going to attach alligator clips to each. The colour of the alligator clips doesn't really matter. There we go, one to each. Now what is going to be important is that we know which one we're attaching which metal to. I've already decided that copper is going to be the cathode and that zinc is going to be the anode. So what we're going to do is we're going to attach the copper to the positive and we're going to attach the zinc to the negative. So that's the negative and that's the positive, right?
Yes, it is.
Okay, so that's the positive. It's going to attach that over there, and he's going to attach now the zinc to the negative. There we go. He'll put that over there as well. Alright. So we can put the copper on that side, the copper will be on the left, zinc will be on the right. He's going to turn it on, he's going to put it on the 20 setting here. They're all different. You might have a 2 setting. If you've got a 2 setting, you should use that, but 20 will be fine for this one. Alright, so go ahead and put that down. Let's go ahead and put the solutions on. Now you'll notice what I've done here, or what Sam's done here, is he's got 2 bits of filter paper and he's put them onto a watch glass. And I think that's better than putting them on the bench. So at the moment what he's doing is he's putting 1 molar, 1.0 molar copper nitrate on one side and then 1.0 molar zinc nitrate on the other side. And now what he's doing is he's putting potassium nitrate, sort of joining both of those solutions together. Now what he's going to do is he's going to touch, Taylor, can we have your assistance please? Could you please touch the zinc to the zinc solution here? Oh, okay.
Oh, I haven't.
Ali, if you do, could you do it please? Could you touch the zinc to the zinc solution, zinc side? Here we go, that's right. And you can see, could you please move the multimeter up a bit? There we go. And you can see that's giving a reading now. So in this part, this is how you're going to determine what solution concentrations you're going to use for each part of the Nernst equation, or the non-standard cell solutions. So this is the Nernst equation here, E cell, E naught cell minus RT, NF, ln of Q. And the E naught cell is what you calculated earlier, and you used that to determine which one was going to be the anode and the cathode. We agreed earlier that copper was going to be the cathode, so that was going to be undergoing reduction. Zinc is going to be the anode, that's going to be undergoing oxidation. When we add these 2 reactions together, you can see the electrons will cancel, we'll be left with this. Copper 2 plus zinc gives zinc 2 plus copper. The Q here is the reaction quotient, which will be zinc 2 plus divided by copper 2 plus. Now Q then is going to equal the concentration of zinc 2 plus over the concentration of copper 2 plus. The metals will be ignored here because they don't have any concentration associated with them. It says specifically in the lab manual that we need a value of E cell that's lower than the E naught cell value, which means that this value here is going to have to end up being subtracted from this to give something less. If zinc 2 plus is bigger, we make that 1, and we make copper 2 plus 0.1, then that's going to come out to be log of 10, which will clearly be a lower value once we calculate E cell. E naught cell minus this value will be lower than E naught cell by itself. So then from there we know that zinc 2 plus has to be 1.0 and the copper 2 plus has to be 0.1. So when we're looking at the Nernst equation, the E naught cell is going to be that calculated standard cell voltage that you got earlier. And then you've got your N value, which is going to be the number of electrons transferred in the balanced equation. Now what we're looking at here is the zinc giving up 2 electrons and then the copper 2 plus accepting 2 electrons. So the number of electrons transferred is going to be 2, so N equals 2. The temperature is going to be assumed to be 298K, and R and F are in the lab manual in the background section. I just wanted to show you a wrinkle with the copper and the aluminum. What happens with those is one's 2 plus and one's 3 plus, so we need to balance that out, and we do that by multiplying this one by 3 and multiplying this one by 2. Notice when we multiply the equations though that the voltages don't change. The only thing that changes is going to be the coefficients here. Now we figured this out, and you can see that n is going to equal 6. That's the number of electrons transferred. It's going to be 6 on each side, 3 times 2. The Q value also is going to change. It's going to be Al3 plus squared and Cu2 plus cubed. And that's going to affect the value of Q that we end up with as well. But it will still end up giving a lower cell voltage theoretically than what we started with.